that should be disastrous for people who do not understand or realize that it is a disaster yet. Yes, I just said that. Which to me is, well, that is not a good thing. All right. So what shall we do today? Okay, I'll give you choices. And I realize that in many of my classes, my students actually do not like choices. They want the class to be like a train on a track. It is not. There's no deviation whatsoever. I tend to conduct my classes like a dune buggy. It's like, where do you want to go? We can turn around. So what we can do, at least there are two options. One, we can finish Dijkstra's algorithm. Okay, I think that actually might be a good thing to do, so we can see how it terminates. Or if you guys say, okay, I get it already. I went home, I finished the whole trace by myself, reading the instructions, and I get everything that is to get with Dijkstra's algorithm, then you guys can go like, okay, let's not do that. We can move on to A star algorithm. So which way shall we proceed? Hmm? Finish Dijkstra's algorithm? So how many of you, yes. Okay, so you're supportive of Dijkstra's algorithm. All right. So did you spend any time to at least follow the algorithm up to the point where we kind of stop, or because that's kind of important, okay? That is kind of important. All right. So what we'll do is we'll continue with this, and I kind of need a picture of, what the values are. So let me do that. Uh, where is it? Nope, here. All right. So what I'm gonna do is to take a picture of this, kind of display on one side so we can tell the how the vertices are connected. Okay, like so, and then switch back to this slide over here. All right, so let's say we are over here. So the vertex that we have chosen to take a look at is vertex D, which means we have to take it out of the set queue. That's at the beginning of the while loop. And once we do that, we look at all the incoming edges to D, which means we're looking at all the arrows ending up at vertex D. There are two. I already did that yesterday, because vertex C goes to vertex D. Vertex F is also going to vertex D. So that's why I kind of pre-populated these two rows with C and F. So now we have to evaluate, is vertex C finding a shorter path to a destination through vertex C? That is the question. So now we have to first evaluate what is the length of the shortest path from vertex D to a destination. According to the L value of vertex D, it is 2, okay, which is pretty low already. So now we want to ask, if vertex D is to go through vertex C to go to a destination, what would that be? Vertex D has a value of 2. Oh, I take it back, it's the other way around. We have to look at vertex C. Okay, vertex C to go through vertex D to get to a destination. So we're looking at vertex C to go through vertex D to go to a destination, which in this case is destination F itself. And we want to ask, is that going to be a shorter path? So the answer to that question is yes, it is, because the way we calculate that is to look at, okay, what is the length of the shortest path from vertex D to the closest destination? That would just be L of D, which is 2. Then we have to add to that the distance from C to D, which is a 4. So 4 plus 2 is a 6. So that means if we are to go from vertex C through vertex D to the closest destination, it would be a length of 6. The length of the shortest known path from vertex C to a destination is 8 because of this particular edge here. So that means we just found a shorter path. So when you find a shorter path, there's a bunch of stuff you need to do. The first one is to update the actual L value to the current to the length of the shorter path this time. And then you have to go here and then you make some adjustments to this particular set. And the way we make those adjustments is to add the new edge, which is from C to D. But then the other edge leading out from vertex C, which is from C to F, that one we have to strike out. Or, in your case, if you don't like striking out, you can just delete the whole thing altogether. So this is how we are making changes to E prime, which is the solution of running the algorithm. And because we just found um, a shorter path from vertex C to a destination, so vertex C needs to be added to the set Q. It is already in the set, so but it is okay to mention that even with the update, the set Q looks exactly the same as before. So now we look at vertex F. So vertex F itself is a destination, but it does have a path to go to vertex D, has an edge to go to vertex D. So we go through the same calculation. Yes, that is a question that I will answer with a very annoying answer, as usual. Okay, most of you already know that I like annoying answers because I said so, because the algorithm said so. So this means it is super duper important that you guys study before class. Okay, you need to at least know where to find the algorithm, and that would be here. Just scroll up a little bit. Okay, go back to Dijkstra's algorithm, and they're all described here. So that's what you guys need to do before class, because otherwise, it would be kind of difficult to understand what I'm doing and why I'm doing it. I mean, okay, so what I'm doing is can be answered with the algorithm itself. Why I'm doing it is what you really need to focus on, because once you understand the rationale behind doing something, then it would not be difficult to remember what it is. So, is that okay? All right. So removing it is from this line here, and so that means you're understanding this code, this pseudocode here is really important. Right. So where were we? Okay, going back here. This is also why I like tracing algorithms using this representation, because I can basically take a break, pause anytime, I can come back and resume the tracing. Yes. Mm-hmm. So L of V is from D to the closest destination, so that would be the 2. So the D is from C to D, which is a 4 based on the graph here. So because we are looking at this edge here from C to D, because the bottom line is what is the length of the path of from going from vertex C to vertex D, because and then from vertex D to the destination. And the question is that a shorter path compared to the path that I have discovered already? And huh? L of Yeah, so if you look at the variable W, L of C was an 8 earlier. That is correct. I just changed it to a 6 because I'm already done with all the update steps. All right, so now we are evaluating what if we are looking at the incoming edge of FD. So when we look at FD, you go like, oh, but F is already a destination and we don't have to do anything. Well, when you're following an algorithm, you don't think like that. You just follow the algorithm, which means you go to L of F, which is a 0, and then you go to L of D, which is a 2, and then you look at the edge from F to D, which is a 2. You add 2 to 2, which is 4, and then you ask, is 4 less than 0? The answer is no, so that means we don't have any updates. Okay, so that's my general recommendation is not to look at things from the perspective of, oh, we know it's a destination, we don't have to do anything, but really just kind of follow the code exactly and then do what it is suggesting you to do. Because otherwise, if you try to follow an algorithm, but using intuition instead of using the actual logic that is specified, sometimes it will lead you the wrong path and you end up doing something that is deviating from what the algorithm specifies, so that would not be good. All right. So now we are at the beginning of the while loop. Okay. The while loop says, is Q empty? No, it is not empty. It has two elements in it. So now we have to go for another while iteration, which starts with, let's pick one element out of Q where the L value is the least amongst all the choices within Q. We only got A and C left in Q, so we are looking at the L values of A and C respectively. A has an L value of 7, C has an L value of 6, so C is going to be the one that I choose. So once I choose vertex C, we have to remove it from the set Q, and now we look at all the incoming edges into vertex C. Vertex C does not have any incoming edges, so that means the for each loop has nothing to do. So that means we are now back to the beginning of the while loop. The while loop says, are we done? Nope, we are not done because Q is still non-empty. So now I have to choose the vertex from Q where it has the least L value. Now, obviously, that is super easy because it only has one vertex left. So we pick A out of the set Q. Q now becomes empty, but we are in the loop body already, so we cannot just like, oh, we are all done. No, we are not quite done yet. So now we have to look at all the incoming edges to vertex A, and vertex A does have one incoming edge, which is come from vertex B. So now we have to go through that calculation. So we have to ask, okay, vertex B, what is the length of the shortest path to a destination right now? And we look up the L value of V, it is 2. Okay. And then what we do is we say, okay, what about you, vertex A? What is the length of your shortest path to a destination? It is a 7. Okay. But the algorithm, says you still have to kind of compare, right? Because you already know, the answer is going to be a no, but we still have to do the calculation, which means we look at the edge BA, which has a value of 4, and then we add that to the L value of A, which is a 7. 4 plus 7 is 11. And then we compare 11 to L of B, which is 2. And clearly 11 is not less than 2, which means we don't have anything to do. So that means, now we go back to the beginning of the while loop. The while loop says, is Q empty? Yep, Q is empty at this point, so we are all done. So that concludes the trace the of Dijkstra's algorithm. All right. So now the bigger question is, so we are done with the algorithm. What is it giving us? So what it is giving us is E prime. So E prime really is the answer to the whole thing. So it says that DF is on the path of shortest paths, in this graph. And you can see how DF is highlighted. Okay, it is highlighted here. It says that BE is also along the shortest path of some vertex, and you can see how BE is also highlighted here. AB is the same way, okay? This is highlighted using a thicker arrow, and then CD is also the same way it is highlighted. So that means all the thick arrows are representing um, edges of shortest paths. So that means, um, so back to the example of Six Flags, these are the bathrooms, right? And these are the possible intersections, within, Six Flags, the locations. So let's just say that, oh, okay, you're done with watching the dolphins doing their tricks, and that corresponds to vertex B, and you ask, and then one of the first graders is asking you, oh, I need to go to the bathroom. Well, you just follow whatever is the thick outgoing edge, and that will lead you to the closest bathroom. In this case, it's right next to it. You just take one particular edge, and then you'll be at the bathroom. So that's how this whole thing works. Or if you somehow end up in vertex C, okay, and one of the kids says, I need to go to the bathroom. Well, in that case, you have to follow this edge here, which ends up at vertex D, and then from vertex D, you also follow the thicker arrow, which is this one here, and that will lead you to one of the bathrooms, the closest bathroom from the perspective of vertex C. Are we doing okay so far? Okay, does everybody know how to make use of E prime? How E prime is really representing the shortest paths from every vertex to the closest destination from that particular vertex. So we good? All right. So this is kind of interesting because it really contrasts with the original Dijkstra's algorithm, which is taught in CISP 430, because that one, it goes from the origin to a single destination. This one starts with all the destinations and work its way back as far as possible to all the vertices. But they are both Dijkstra's algorithm. This one is just a slightly modified version of the original Dijkstra's algorithm. So are we good? Yep. Yeah. The strikeout is just me visually showing you, what should be deleted in the process. So the actual answer would be the ones that are not struck out. Yep. Yep. A heap is usually better because because this is quote unquote a greedy algorithm. So when we have multiple vertices in Q, we want to choose the one with the least L value. So that means a heap is a better choice because a heap automatically keeps track of the smallest or the largest item within the collection. So it would lead to a faster implementation. If you are to use a queue, then you still have to search through and find the smallest element. So that increases the time complexity a little bit. All right. Any other questions regarding Dijkstra's algorithm? Yep. Um, I'll let you guys think of more examples. Okay, you can generate a graph. Okay, tell me where the destination is and how the connectivity between the vertices go, distances, of the edges, and I'll be more than happy to kind of work that out. If you want to go from A to D, well, there's no such thing as from A to D. It is always from A to the closest destination. So you follow the thick arrows, it goes to B, and then B goes to E. Because we consider all destinations to be equivalent. So you just need to find the closest destination. Is that okay? All right. So for anyone who want me to go through a different example, you're welcome to come up with a different graph, and I'll be happy to kind of work with the graph that you create, and we'll work with that. But until you have a specific graph that you want me to kind of go over, I want to go over the A star algorithm, if that is okay. All right. I think some of you want me to go over another example, and I think the underlying reason is you're not quite sure how to read the instructions. Is that correct? And so in that case, instead of going through another example, which may or may not help explain the steps, why don't I just ask you which line needs clarification? I know they're not numbered, but you can try to identify the line so I can look at that line and go like, okay, this is what that line is trying to say. Yep. You mean this one here? Okay. Uh, the L values are initialized here and they are updated here. And if you're asking me what the L values are representing, I believe they are explained up here. The L value is basically the length of the shortest path known up to a certain point of time. And the actual, what this particular statement is trying to do is sort of explained here. So we want to find a vertex v in the set Q so that among all the vertices in Q, vertex V has the lowest value for the L value. And this is also why Dijkstra's algorithm is also known as a greedy algorithm because it is optimistic. Any other questions? Hmm. Okay, so let's look it up again. Okay, so all right. So the way you do this is to look up the exam final schedule, final exam schedule. You go to spring 2000. Okay, they fixed it. So it's now actually just your spring 25. This is a daytime class, and then you look it up. Well, since I'm here, might as well just finish looking it up. It's a Monday, Wednesday class. Our lecture starts from noon. So it is, according to this, May 19th from 12:45 to 2:45 p.m. So this particular entry matches this class, unless I make some really stupid mistake somewhere. Are we good? All right. So put it on your calendar. Make sure you don't forget, okay? Even though the start time of the exam is 45 minutes after the usual start time of the lecture, you still want to kind of make sure that you remember to show up on that day to take the final exam. Yeah. What do you mean by that time? I'm talking on Zoom. Um, I must have looked it up incorrectly because I think this is correct. So use this time, as the exam time, not the one in the syllabus. Yeah, May 19th is our exam from 12:45 to 2:45 p.m. Hmm. All right. So we good on the final exam time and date. Good. All right. It is open book, open notes. If you find all the previous exams, you can bring those with you too. Although I'm not sure how much that's gonna help. Sometimes it hurts a little bit. Other times it helps. So it's all it, situational. All right, so we're going to move on to the A star algorithm. So the A star algorithm is a little different from Dijkstra's algorithm in the sense that it has a heuristic function in it. Okay, we make use of what we call a heuristic function. The best way to understand why these two algorithms are different is to think about Dijkstra's algorithm as a breadth first search type of algorithm. In other words, it expands from either the starting point or the destination outward in basically concentric circles until it touches the other vertex. Okay, I'm talking about the one that has one single start and one single destination. But nonetheless, it is a breadth first search algorithm. Um, if you're not interested in finding all the shortest paths from every vertex to a destination, then it may not be economical to use Dijkstra's algorithm. Think of the that you're driving, okay, and you want to find the shortest path from, let's say, ARC to San Francisco downtown, okay. Do you really need to know, all the other paths in, say, Minnesota or New York City? No, probably not. Okay, so that means, even though Dijkstra's algorithm is kind of cool in the way that it finds all the shortest paths at the same time, once the algorithm is done, especially the one that I have modified, it doesn't really make sense, in a practical sense when all you want to do is to navigate from Sacramento to San Francisco downtown. Um, you don't really need to do all the computations of on every single road in the United States. Okay, so that's one. Two, even if you use Dijkstra's algorithm in CISP 430, Dijkstra's algorithm would do a what we call, what I already said, a concentric expansion. In other words, if you use Sacramento or ARC as the origin or the starting point and San Francisco as the destination, it would basically do a concentric expansion of the exploration. So it would go to Auburn, okay? It will go to Placerville. It will go to Pollock Pines and so on, which in many ways does not make sense. But that's how the algorithm works. Is that okay? I mean, you might need to go eastward a little bit before you get onto the highway, right? You might need to go north a little bit to get onto Interstate 80. So you might need a small detour in quote unquote the opposite direction, but not all the way to Auburn, not all the way to Placerville, and surely not all the way to Lake Tahoe. Does that make sense? But Dijkstra's algorithm would do exactly that. It would do concentric expansion until the destination is touched. So from that perspective, it may not be the most efficient way of finding the shortest path. So the way the A star algorithm deals with this is it introduces a heuristic function. So the heuristic function is described here. It is a function. Okay, this is the function notation. The domain, yep, it would use the heuristic function to quote unquote lean in the direction of the destination. So the best way I can describe it using just colloquial term is it has a leaning tendency so that things that are too far away, it goes like, no, there's no way Auburn is on the shortest path from Sacramento to San Francisco. So that's how it works. But how does it know that? It is the job of the heuristic function. So the heuristic function, to describe what is the domain and what is the codomain, this is the domain. The domain is really just the Cartesian product between all vertices and the single destination. So A star can only handle one single destination. It cannot handle multiple destinations. So this means the what you need to provide to the H function would be a tuple. It's a two tuple of the vertex, a vertex, and the destination, and then the domain or the codomain is would be all the non-negative real values. So that means you cannot have a negative value for heuristic, but you can have zero as a heuristic value. When the heuristic value is zero, the A star algorithm, quote unquote, degenerates into Dijkstra's algorithm. In other words, when there's no leaning tendency, then it would basically go back to the default behavior of concentric expansion until it finds the destination. But if you have a really good heuristic function, then it would do a really heavy leaning to the destination and not to go beyond. For instance, in the case of the map that I'm talking about here, it might go as far as Madison, okay, where it intersects with the highway, but not much beyond that. So it would basically, instead of I'm drawing something on the board here, unfortunately. So instead of trying to do the concentric expansion here, it would do more of an elliptical expansion like this toward the destination. That's what the heuristic function is supposed to do. But if the heuristic function is just zero, then it would do the concentric expansion again. Yep. It doesn't really help that much if you expand from both ends. You can, but it doesn't really help that much. The heuristic function is always going from a particular vertex to the destination. That's how the heuristic function typically works. But you can always define it so that you can find a heuristic value between any two vertices. So yes, you can expand from both ends, but typically it does not help that much. Hmm? Well, then how do you determine when to continue the expansion from the destination and when do you expand it from the origin? But how do you know which side to expand more? Or do you expand a little bit here, expand a little bit here, expand a little bit here, expand a little bit here? You can, well, I mean, you can, but it complicates the algorithm, but I don't think there's a lot to gain. You can give it a try, right? You can try an implementation of the A star algorithm where it expands from both sides and see whether it is actually faster. Both of these are really just ways of doing things. There are definitely ways to quote unquote defeat it. So we'll take a look at that. All right. So now we're going to describe the actual algorithm. Remember, all the let blah 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 is really the input to the algorithm. So in this case, we need a graph. Okay, so we need to know where are the vertices and also how the vertices connect to each other using edges. Okay, so that part is exactly the same as Dijkstra's algorithm. The second part is a distance function. For every edge, we need to know what is the distance of that particular edge. That's also the same as Dijkstra's algorithm. The third one is starting to deviate a little bit. So in A star, we need to designate a single start vertex. So this is different from Dijkstra's algorithm. We also need to designate one particular destination vertex, which is also different from Dijkstra's algorithm, at least the one that I talk about in this class. And then last is we need a heuristic function. I forgot to update this one. It doesn't need to be a Cartesian product from vertices to all vertices. It just has to be a Cartesian product between a vertex with the destination. So, this is the way it's described here is not wrong. It is just a lot more than what you need. Okay, so those are the inputs, and this is the algorithm itself. You start with some initialization. So the initialization is saying for each vertex in V, we have to do the following. If V is the start vertex, if V is not the start vertex, we have to do these initialization. Otherwise, we have to do these initialization. So explanation, G of V is the actual length of the shortest known path from vertex S to vertex V. That is how G of V is defined. It is initialized to infinity for anything that is not from the start vertex, because until we explore, we cannot even know whether vertex V is even reachable from the start vertex. And that's why they're all initialized with infinity as a value. Basically, in order to express the fact that we don't even know whether we can get to vertex V from the start vertex, so we'll just put an infinity here. The second one is the F value. The F value is a little bit more confusing. It is an estimation, okay? It's the estimation of the length of the shortest path from the start vertex, which is vertex S, through vertex V to the destination. Okay, so the first part is exact. Okay, from vertex S to vertex V, that is just G of V. The second part from vertex V to vertex X is estimated by the heuristic function. So we'll talk about the heuristic function in just a little bit. So essentially, f of V is G of V plus H of Vx, because X is representing the destination vertex. Yep. Say that one more time. Um, Yeah, so h of the 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 h function, h of vx, is basically how you're leaning. So if h of vx is the actual length of the shortest path from v to x, then you have the most extreme case of leaning, which means you're not going to explore things that cannot be on the shortest path. On the other hand, if h of vx is 0, then you have quote unquote no leaning tendency at all. Then you end up with a concentric expansion again. Yep. Sure. All right. So that explains what we do in terms of the initialization for every vertex v in the set V that is not the starting point. What if V is the starting point, which is what this else is about? Then G of V is going to be a 0. That's because G of V, in this case G of S, is telling us what is the length of the shortest path from vertex S to vertex V. But when V and S are exactly the same thing, we're really asking what is the length of the shortest path from the start vertex to the start vertex itself. Well, are you surprised that we initialize it to 0? Yep, exactly. Okay. F of V is really just h of Sx because because g of v is 0, and also because we know f of v is g of v plus h of vx, so we just have the second term left because the first term is a 0. So are we doing okay so far in terms explaining all the way up to here? That's just for initialization. Okay, all right. So now we move on to the last little bit of initialization. So instead of keeping track of E prime as the solution, the way we keep track of, okay, so what is exactly the shortest path? We keep track of all of that using a previous. So from CISP 430, you guys have learned about a doubly linked list, doubly linked list. So previous is really kind of borrowing that kind of mechanism. So we only keep track of, oh, in order to get to vertex V, where are we coming from to get to vertex V? So that's the only mechanism that we need in order to keep track of the shortest path. Is that okay? So that is initialized to undefined for every vertex V because for every vertex V, we really don't know where we should be coming from, at least initially. And then the last thing we do before we start the loop is to initialize a set O to only consist of the element that is the start vertex. So that's how we start the whole process. Are we still doing okay so far before we get to the while loop? Okay, so this is the while loop. Okay, the while loop, the condition of the while loop is more complicated compared to the condition of the while loop in Dijkstra's algorithm. So now we have to look at this particular quantified expression and ask, what is it really saying? Okay, there, as long as there exists at least one element in O, the set O, such that f of v is less than the g value of x, which is the destination, then we have at least one more iteration to go in the while loop. In other words, it is really saying if there's a possibility that there exists a shorter path, we should not give up yet. That's basically what it's saying. And to map the notation here to what I basically commented here, you have to remember what f of v is representing and what g of x is representing. F of v is the estimated length of the shortest path from the start vertex to vertex v and then to the destination. But a part of it is an estimation. G of x is the length of the actual shortest path from the start vertex to the destination. So that means if all the f values for all the v's inside O are greater than or equal to g of x, that means none of them has a possibility of a shorter path. Because a heuristic can only underestimate, it cannot overestimate the actual distance. That's one of the requirements of what qualifies as what we call a admissible heuristic, is that it cannot overestimate. Are we still doing okay so far? Okay. So now we move into the algorithm, which resembles a lot of this structure, resembles what we already know about Dijkstra's algorithm. So the first one is we practice, this whole thing again, which is the greedy algorithm component of looking for the most promising candidate within the set O. So in this case, we choose C in O such that for every W in O, f of C is less than or equal to f of w. So we are basically once again looking for the most candidate to expand, okay, which is what greedy algorithms do. And then we remove c from O, just like we remove v from q in Dijkstra's algorithm. And then we also look at every neighbor of c, but this time we are looking at the outgoing edges, not the incoming edges. So for that part, it's different. So the direction of expansion is exactly the opposite compared to Dijkstra's algorithm, at least the one that I talk about. So now we look at all the outgoing neighbors of n, excuse me, of C. In other words, we look at edges Cn in the set of edges, and this time I use T to store the temporary result. So what T is really representing is G of C plus D of Cn. What is that? What does that mean? Well, we go back to the meaning of G of C. G of C is the length of the shortest path from the start vertex to vertex C. That's what G of C is representing. What do you get when you add the distance of the edge from C to N? Oh, you're just calculating the length of another path from the start vertex, but this time to vertex N. That's what T is representing. So now we compare T against G of N. In other words, we have another way to get to vertex N. We already know the length of the shortest path up to this point from the start vertex to vertex N. If T is less than N, or less than G of N, that means we just found a shorter path from the start vertex to vertex N. So we got stuff to do, okay? We got stuff to do, which is not different, that much different compared to what we did with Dijkstra's algorithm. We perform a union so that we add n to O because if n is if we are finding a shorter path from the start vertex to vertex n, then we might also use vertex n to find a shorter path for things where n connects to. So that's the whole idea of why we want to add vertex n to the set O so that we can add it to the list of things to explore because it seems like it would be helpful. Okay, and then the next one is to keep track of how did we get to n to begin with? It used to have a value before, but now we update it to C because we just found out that whatever that was before did not give us the shortest path from the start vertex to vertex n because you're going from the start vertex through some path to vertex C and then from C taking that edge to n is the shorter path. So that's why we have to do this. So this part here is almost exactly the same thing as the way that we updated E prime in Dijkstra's algorithm, but we don't need a whole set in this case because we are not interested in maintaining edges of all the shortest paths from every vertex to the closest destination. In this case, we're only interested in one single shortest path from the start vertex to the destination. So as long as I can keep track of all the previous links from the destination all the way back to the start vertex, we're fine. We can keep track of the shortest path that way. Next line. We update g of n to be t because g of n is supposed to be the length of the shortest path. And since we just found a shorter path, we'll just update the length of the shortest known path to reflect that. And we also update f of n. So you can see that f of n is really not necessary because this is the definition of f of n is it is g of n plus the heuristic from n to the destination. So that means if you don't want to keep track of the function f, you can always recompute f of something from the heuristic function. You can always do that. The only reason why I keep track of f of n here is it is easier for me to pick an element out of O when I just need to find, okay, who has the smallest value? Just makes it a lot easier this way. All right. So other than that, when we reconstruct, the graph using this mechanism, then we are just reconstructing it so that I have to modify this a little bit because it also adds some extra stuff to it. But basically, we're using the previous function to reconstruct the shortest path from the start vertex to the destination. That's basically what this part is doing. So are we good so far? Just kind of an overall understanding of how the algorithm works. So just from that description, do you guys notice that it shares a lot of elements with Dijkstra's algorithm, except this one kind of takes into consideration of this kind of mysterious heuristic function. So we good? Okay. So I want to mention one more thing before we trace an actual uh, example, which is in the case of mapping. Okay, so let's just say that we are talking about Google Maps. Okay, and I want a heuristic function, for that particular application. The best or one of the best heuristic function is really just the distance of a straight line between 2 points, because it is guaranteed to be it cannot overestimate. The only time a straight line as a distance can be an overestimate of the actual distance that you need to travel between 2 points is when portals are real. Portals, yes, as in the game. So until portals or wormholes are reality, we don't have to worry about that. So the length of the straight line between 2 points when you're doing physical navigation is the best heuristic function because it's also easy to compute. Okay, you don't, the computation is like almost nothing using your hardware that we have today. Yep. So if you take speed into consideration, then the distance is no longer, the best way. Then you have to you have to look at the actual time it takes to traverse that distance at the quote unquote average speed. And this is also why, in Google Maps, you can kind of change the time of the day, and then it will give you a different estimate and potentially a different path, because the way the distance of the edges work out is time dependent. And I believe that they also take that into consideration when they try to use a heuristic function. So they take the time of the day into consideration as well. It's all the cost, or what you want to use, what you're measuring as quote unquote the distance, also depends on what you're doing. I think what's the name of that show? Mythbusters. They did one show on, is it always better to just take a left turn, or is it better to take right turn, right turn, right turn, right? You guys remember the episode? And do you remember the conclusion? The conclusion is it depends on what kind of vehicle you're driving. No, no, seriously. That was the conclusion. The cost of driving, is dependent on what you're driving. If you're driving, let's say, a conventional U-Haul truck or anything that is large in diesel, idling is expensive. Okay, but if you're driving an EV, idling is like you're running the AC and that's it, right? So I think that was the conclusion of that particular episode. Was if you're driving a truck, a delivery truck, at the time they're all diesel or natural gas, um, it might actually be less expensive to do right turn, right turn, right turn. But if you're driving a Prius, it is not worthwhile to take all the right turns to make a left turn. That's how I remembered it. I could be wrong. All right. So if everything is okay at this point, we're going to go to this example here, and I'll tell you guys how to read this. Okay, for the most part, you already know how to read it. If you see an arrow from, let's say, E to A in this case, it is an edge. The number on a solid edge is the actual distance of that particular edge. The only thing that is extra here are the dotted lines. So the dotted lines are representing the heuristic value from a vertex to the destination. And in this case, you can also see how F is the only one that is a circle. Everybody else is kind of like a rounded rectangle. So vertex F is the only destination in this case. Vertex E, if I remember correctly, is the start vertex. So do we have any questions of how to read this kind of pictorial representation of a graph that also tells you the heuristic value between a vertex and the destination vertex? So we are good. We understand what the values are. Yep. From which to F? From D to F. Oh, that means the heuristic value from D to F is in fact a zero. You can do that. The heuristic value can be a zero because zero is guaranteed not to overestimate. Yep. In fact, this one is 20. This is not a heuristic, it's a solid line. So this is the actual distance of the edge of DF. And you can also see, how the dotted lines go straight from E to F. There are no edges directly from E to F. But heuristics is not about edges. Heuristic is about quote unquote the whole path. So even if a vertex cannot reach the destination, you can still give it a zero as a heuristic because as long as you're not overestimating, you're still fine. So are we understanding, what the dotted lines are representing and why we have dotted lines when there are no solid, edges between two vertices? We good? All right. So what I'll do is I'm gonna kind of decrease the magnification because otherwise this takes up way too much space on my screen. So before I take a screenshot of this, okay, so take a screenshot and display that so that I can kind of keep track of what I'm doing here. Okay. And then I go back to the folder where oh, okay, I have to kind of go back to that folder. So this is going to be in the shared folder. There's a template for the A star algorithm. It's called A star template. Okay. And oh, okay, that's not what I intended to do. I intended to make a copy of this. So make a copy. There we go. And I will name this copy using today's date, 2025-05-07. Oops, okay, just type 0507. There we go. Okay, alrighty. And it has edges all the way to G and J. Okay, that's fine. We just don't use those two columns, okay, because we don't have enough vertices to use everything here. But it is set up in basically a similar way as the other one. And this is going to be a larger table just because we got more things to track. All right, so do you guys, so vertex E is the starting point. So that means vertex E is the only one that has a zero value when it comes to the G value. So G of E is a zero. And then everybody else, oh, okay, I'm not supposed to change that because that's actually calculated. I'm supposed to change starting from the row 4. So there's a 0 here, and then everything else would be infinities. I used to remember the Unicode of the infinity symbol, but I don't anymore because I got some other stuff that I need to remember. All right, so 1, 2, 3, 4, 5, 6. I think we got everything initialized here. And then the F value, kind of the same thing. Vertex E is the only one that has a non-infinity value. In this case, it will be 13 because that's the heuristic value from E to F. That's why this is a 13. And then everybody else is going to have infinity, except for F of F. Okay, actually, yeah, no, they're all infinity. There we go. So they're all infinity here, and then 4 more infinities to go from here to here. And just to make the diagram easier to read, I'm going to hide these two. So we just hide KL, and doesn't like it because I set with protection so that I don't make random changes that can be bad for the spreadsheet. So we hide those two, and then we also hide these two. And there we go. All right. And then the previous are all unknown. So I'm going to use UNK to represent unknown. And that goes all the way to here. And then O is initialized to only consist of the start vertex, which in this case is vertex E. So this is how everything is initialized, and this is the graph. And I just want to make sure that we show the graph and also the how everything is initialized. Do we have any questions at this point about the trace? Yep. Um, okay. So how is f okay, so are you talking about, the f value of a should not be infinity, or are you talking about the g value? Hmm? The f value? Okay, so how is the f value defined? Okay, you can actually read the algorithm from your computer. So how is the f value defined? But how is it defined? Actual definition. Okay, let's find it. So right here it says f of v is g of v plus h of vx. So if we know g of v is already infinity, what happens to f of v? It's also going to be infinity, right? So that's why when we trace this thing, this is the previous one. I can close that out now. And this is why, if the g value of something is infinity, the corresponding f value is guaranteed to be infinity because it would be the infinity plus something, which is still infinity. All right. So now we can start the algorithm. The algorithm says, in order to stay in the while loop, it is saying, okay, look at all the vertices in the while loop. Can I find at least one of them having an f value that is less than the g value of the destination? The destination in this case is vertex f. Okay, so I'm just going to boldface f here so that it stands out and be remember this is our destination. Okay, there we go. So we look at the f value of the element in O. In this case, there's only one, which is E, and the F value is 13. And we compare that to the G value of our destination, and our destination is vertex F, which has a G value of infinity. So the question is 13 less than infinity? Okay, well, it satisfies the existential quantifier. We have to stay in the loop. Does that make sense? Because at least it looks like one we might be able to find a shorter path to the destination from the origin, from the start vertex. That's the rationale of the condition of the while loop. So once we get into loop, yes, mhm, you only have one heuristic function, so that means you only get one heuristic value. Yep. All right, so we get into the loop, and the first thing we do is, okay, vertex E, you are chosen because you're the one with the least f value, and then we have to remove it from the set O. Okay, so O is now an empty set, and then we have to now look at all the outgoing neighbors. In other words, we're looking at outgoing edges or arrows going out of vertex E, and include all of these here. We got two, right? Oh no, we got one only. So we have only one here from vertex E to vertex A. So A is the only outgoing neighbor. So we put an A here. So now we need to figure out what is T, okay? So how is T defined in the algorithm? T is defined to be the G value of whatever C is representing plus the distance of the edge from N to C, which in this case is the other way, from C to N. So that means we are looking at the G value of E, which is 0. Very good, because the G value of E is a 0, plus the distance of the edge of EA, which is a 5. 0 plus 5 is 5. Okay. Johnny 5 is alive. Indeed. Okay. So now the next question is we are using t to compare to g of a in this case and see if t is less than g of a. In other words, we because we just found a path from the start vertex to vertex A, and we are asking, is this path from the start vertex to vertex A shorter than the last path or the current path that I know of? Okay, that's basically what that comparison is about. So we are now looking at g of a, which is infinity, which means we have not found a path yet. Okay, this is the first time we find a path from the start vertex to vertex A. So, but in the code, it is comparing t to g of a in this case. Either way, you go like, yep, we probably got a bunch of stuff to update. So we put a 5 here because now we have just found a path with a length of 5 from the start vertex to vertex A. Does that make sense? Okay. Then we also have to update um, f of A. Once again, how is in this case, f of A defined? F of A is g of A, which is now 5, plus the heuristic from vertex A all the way to the destination. So you follow this dotted line here, okay, from A all the way to F, it is also 5. 5 plus 5 is a 10. So that means f of A is updated to a value of 10. Are we good so far? So since all of you have computers in front of you, I highly recommend your computer to stay on the algorithm itself because you probably still need to reference the algorithm from time to time to know what we are doing. So that would be kind of helpful if you have the algorithm in front of you. I can also kind of flip-flop between this screen and the algorithm, but I think that might actually cause more problems than it solves. So but you can vote as a class. You can vote and go like, Tech, we want all the flip flopping. Then I can do all the flip flopping. No, okay. I don't see anyone who's saying, but I really want that flip flopping. Okay, all right, cool. We also have to update previous. In other words, to get to vertex A using this new shorter path, where am I going from in order to get to vertex A? You go like, okay, we're coming from vertex E, so we update that. And then we also have to add vertex A to the set O because we just updated the G value of A, which means, we just found a shorter path to vertex A. So maybe through vertex A, I will also find shorter paths to all the vertices that A connects to. Does that make sense? Okay, so that's what we're going to do. Put A into the set O, and we are now done with the for each loop because E only has one single outgoing edge to A. Is that okay? So now we start the next while iteration, starting with asking the question of, are we done? Okay, because if we're done, then I'm good, and you guys can, we can end the class 15 minutes or 12 minutes ahead of time, and I'm not going to give you the refund for that extra 12 minutes, and we are good. Okay. Unfortunately, we're not ready to end the algorithm yet because the while loop is asking, uh, looking at all the vertices in the set O, does at least one of them have a f value that is less than the g value of the destination? The g value of the destination, which is vertex f, is remaining to be infinity. And then the only element in O is vertex A, which has an f value of something other than infinity. I think that is enough to say, darn it, we're not done with the while loop yet. So now we have to go, okay, fine, it's okay. We just say, okay, we're going to choose vertex A, to be our variable C, take it out of the set, okay? And then we look at all the outgoing edges from vertex A and go like, okay, who are the neighbors of vertex A? Well, there's a whole bunch. And the order in this case is not important. So I intentionally is just going to go like all over the place to emphasize that there's no particular order you have to go when you look at the outgoing edges of vertex A. You just Make sure you keep track of all of them, but the ordering is not important. But then we have to go back to each and every single one and compute the value of t for that particular one. So the value of t is g of a plus the distance from a to d. And g of a is 5. The edge from a to d is 2. 5 plus 2 is a 7. Okay, so we put a 7 here. And then we compare t to g of d. G of d is currently infinity, and we are comparing that to to 7. 7 is less than infinity, so we go like, oh, okay, we just found a shorter path from the start vertex to vertex D. Okay, so we got a bunch of stuff to update now. This is going to be 7, and this is going to be 7 plus the heuristic value from D to the destination, which according to the diagram is 0. So this is just 7 also. And then to get to vertex D, we are coming from vertex A, so the previous is updated. And because we just found a shorter path to vertex D, we kind of have to add it to the set O just to say, okay, yeah, this may be a little bit promising. Maybe going through vertex D, we'll find the shorter path from the starting point from the start vertex to something that vertex D connects to. Now we do the same thing with vertex B. So we look at vertex B, we try to compute the value of t first. So once again, we look up what is g of A. G of A is 5. And then we look at the distance of the edge AB. The edge AB has a distance of 8. So we are adding 5 to 8, which is 13. So this time t is 13. And then we are now going to compare t, which is the length of the new path from the start vertex to vertex B, against the length of the shortest known path up to this point, which is represented by g of b. Yes, g of b. So g of b is infinity. 13 is less than infinity. So we go through all those updates again. This is 13. This is 13 plus the heuristic value from B to the destination, which is 2. So 13 plus 2 is 15. And then we also have to remember to get to B, it is best to go through vertex A. And because we just updated the value of uh, g of b, we add b to the set O, and now we move on to the last iteration of the for each loop, which handles vertex C, which is an outgoing neighbor of vertex A. Same thing, 5 plus the distance of the edge AC. 5 plus 5 is a 10, so t is 10. And then we compare this 10 to the current g value of c, which is still infinity. 10 is less than infinity. So now we go through all those kind of similar updates. And now this is 10 plus the heuristic from c to the destination f, which is just 1. So 10 plus 1 is 11. And then we say that to get to vertex c, we should come from vertex a. And then we update set O to include c. And that concludes the for each loop. We have now examined every outgoing neighbor of vertex A. So when I said outgoing neighbor, I'm not talking about party animals as your actual neighbor. I'm talking about neighbors of a vertex that are connected by edges going out from vertex A in this case. I'm trying my best to keep you guys awake. That's all. Do you have outgoing neighbors? Yeah, sure, I got outgoing neighbors. All right. All right. So now what do? We say, well, we got about 6 more minutes to go. Maybe it's time to go exit the class. Can we get out of the while loop? Well, the while loop this time is not dependent on whether O is empty or not. Now, clearly, if O is empty, then it's time to get out because then no one in O has a f value that is less than the g value of the destination, right? But It is not empty, so we better go through some evaluation here. Well, turns out to be pretty easy because we are still comparing to the g value of the destination, which is remaining to be infinity, right? And it is guaranteed that everything in the set O has a non-infinity f value. How do we know that? Let me state the question again because I want you guys to kind of think about how can we know that? How can I make the claim that if a vertex is in the set O, that vertex is guaranteed to have a non-infinity f value? Why is that? Okay, okay. So I think you're overthinking maybe just a little bit. So the way we approach this is how do we even get values into f anyway? So the initialization is one. The initialization will only give, it would only initialize f of the starting point or the start vertex with a non-infinity value. Everybody has infinity, right? But the start vertex is also the only thing in O to begin with. So that satisfies the first requirement, which is quote unquote the base case. So it satisfies the base case because of the way we initialize the set O. It is only initialized with the start vertex, and the start vertex is guaranteed to have a non-infinity value. Okay? Then we look at the only place where we can update the f value. The only other place to update the f value is right here. So by the time we get here, what does it mean for the g value? Because the f value depends on the g value. The g value gets the value of t. Okay, so what is the big deal of that? The big deal of that is how do I get t? T is the g value of the vertex before me plus the distance of the edge connecting the vertex before me and myself, right? So now it traces back to what about g of c? How do we know that is non-infinity? Where's C coming from? We choose C from the set O. So you can also kind of get a feel of why proof by induction is really helpful here, right? Because we have a base case because of the initialization, and then we can say if we make an assumption, induction assumption, that for iteration k, the theorem is true, then we have just used that induction assumption to prove that for iteration k plus 1, the theorem is true also. Okay, now this is not a formal proof. Okay, I did not use any symbols. I just verbally described the whole approach. But I hope you guys can get a gut feeling of how proof by induction and loops and proof that a particular property is true for all iterations of a loop, they're all connected. Okay, so getting back to the regularly scheduled program. Yes. So now we look at these three and we go like, okay, which one of you has the least f value? So we just go to each one. Okay, the one is 7, right, right here, and the other one is B, which is 15, and then the other one is C, which is 11. Ah, okay, D wins. So we choose D out of the whole thing, and then we take it out of the set so that we don't, accidentally step on it again and make an infinite loop for ourselves. So now we look at D and say, okay, who are the outgoing neighbors of D? Okay, so here's vertex D. It has one out, well, it has two. It has C and F as its outgoing neighbors. So we just kind of make a note of that. It has F and C. And then for each one, we go through the same evaluation. And in this case, G of D is 7. And then the edge from D to F is 20. Oof, okay. So 27 becomes T. So T is now 27. And then we ask, is 27, which is a pretty high value, is that less than G of F right now? Yep, because G of F is still infinity. So we go like, woohoo, finally, we found a path to the destination. with a length of 27. And this is also going to be 27 because the heuristic from the destination to itself is going to be 0. And then the previous is really just going like, okay, in order to get to F, it is best to go through D. Okay, so D is here. And finally, we add F to the set O. Then you go like, but that doesn't make sense. Tack, this doesn't make sense at all. Okay, because there's no way F, there's no way F of F, okay, which is I'm referring to F function applied to F here, is going to be less than G of F just because of the way it is defined. But if the algorithm says this is how we're going to do it, this is how we're going to do it. Okay. So there's no special consideration when we first touch the destination vertex. We treat it like any other vertices. Okay. No special consideration here. And then we move on to vertex C. We are looking at G of D, which is still the 7. And then we add to it the actual edge uh, distance from D to C, which is a 2. 7 plus 2 is a 9. So we now compare this 9 to G of C. G of C is currently a 10. We just found a slightly better or shorter path, which means, oh, okay, we're going to update a bunch of stuff again. This is going to be 9, and this is going to be 10, and we update the previous of C, and we basically say, oh, in order to get to C, the best way is not to go through A anymore. The best way is to go through vertex D. So that's the meaning behind the update of the previous. And then we go to here and go like, oh, okay, we probably want to add C to the whole set, but C is already here, which is, okay, that means no actual change to it. All right. So if I just continue the lecture until Ryan gets here, are you guys willing to pay extra for that time? Shucks. Okay, we'll continue this next Monday. We got 5 days between today and next Monday. So what do you think is the best thing you can do for this class? Finish this algorithm. Yes, yeah, locate all your outgoing neighbors, sure.